All right. As Steve said, this is the hands-on interactive portion. So I'm going to give you a problem, and based on what we've done so far, I'll give you a little bit of direction, and then I want to. The point of this is to take what I've shown you already about how to take an established piece of code, build on it, and turn that into a very short problem that you can solve and get some results out of. So we're going to be solving just a standard reaction diffusion style equation. So we have a diffusion term, and then a reaction style term with a coefficient inside of or in front of each of them, and then we have a boundary condition where we have a Neumann style boundary condition equaling sigma on the edge of the domain, and then we have definitions for our diffusivity, I guess you could say here again, and then the definition for B and a definition for sigma. And so you've kind of already been introduced to some of this, but what you need to do is to take the shins, and you can do this for sigma. Let's just make it a 1 by 1 dimension square, and then I'll let y'all kind of have at it. Now before we get started, is everybody in here tried to follow the creating your own application instructions, and was everybody successful at doing that? Or okay, so let me go back to the instructions from before. So what you need to do is create your own Moose application, and you name it whatever you want to name it, but start with that first, and then once you get to I'll take the temperature of the room in a couple minutes and see where everybody's at. But you should create it and try to compile. You should just try to run and make sure that test comes back okay. But I'll take a couple minutes and then take the temperature. If you. Yeah. I just kind of look, get blinded by that. I'm more than happy to help. You might have to actually recompile it if you move it. Yeah. So that's why it pays to follow the directions as written. Yeah, that's fine. All right, everybody. So I wanted to see, does anybody need a hint or a way to get started? Like you're stuck, you don't know what's going on, and I'll give you all the hints you need to get started because I want to make it useful and not just staring at a screen for 45 minutes. Okay, so sure. So everybody's past that point. So the first thing you want to do is you look at your equation here. Good. Run test to make sure that everything built correctly. So you want to make sure that that test passes. So that's step 2. Now step 3 is you have your equation here. So the first thing you always do for your interpolation like basis. So you're multiplying through by this function, and you're integrating over the whole domain. So now you have this equation that's multiplied through by this basis function and integrated over the whole domain. And that essentially sets you up for whatever solution to your equation satisfies that equation, the solution globally. But anyway, long story short, you've now integrated. You have this integral equation. You'll want to use you want to manipulate that integral and separate this function out into 3 terms. One term associated with the diffusion term, the first term there. You'll have a second surface integral. That's your boundary condition. That represents your boundary condition. And then your third term here, you don't need to manipulate that. So it'll remain as is. It'll be an integral of that term times your basis function. So after you get to that point, you'll have these 3 terms. Those are the terms that will go into your Moose kernels for your residual. We made a custom version of diffusion that took in a constant, d. But in this case, d is no longer a constant. It's a function of u. So what we did in step 2, or what the code example in step 2, shows you how to create a custom kernel given a constant. You need to create a custom kernel based off of diffusion that is given a kernel that is your answer, your solution, times a coefficient. Similarly to the diffusion kernel, you need to either create a custom kernel that has your solution times a coefficient, or in the Moose framework, there's a code called reaction that does that for you, but it's just you, and you need to inherit from reaction and provide a coefficient. So that gives you, those are the kernel terms for the equation. Now you'll have a third term here. You'll have a boundary condition term. So that boundary condition term, you'll be able to use the boundary condition directly in that term. And so that'll be pretty obvious once you get to it. You're essentially just replacing your boundary condition term with sigma times your basis function. But you'll see that solve this problem. So, in a nutshell, that's what you need to do. Does anybody have questions beyond that, so I can drill down into any specific confusion that anybody has?
So we implement a kernel for D, and then when you try to implement the boundary condition, so then D will be automatically validated on the boundary?
So that's kind of the trick. So add u dot n. You know what that term equals. That term equals sigma. So your weak form term in that case is this. Your weak form term is this times your basis function. So it's sigma times your basis function.
So you just use sigma.
You just use sigma. That's the trick for that term. And diffusion kernel that you inherit from. I would, oh, well,
Maybe go through the, like an example
okay,
through your computer and show like how you set
okay. Yeah, yeah. Yeah. So I'll,
So real quick, so is so the fundamentals are, okay. So the fundamentals are there, it's just how do you put it into the code? How do we put this into? No, that's, and you're probably in good company.
we can solve basically the problem that is already made. We can just mess with that.
So that first thing, can we,
Like define
that's already the residual of something, right?
what? What? By that basis function, then integrate.
Okay, so what are we saying physically? What is that first equation saying physically?
It's so you have some sort of diffusion, some sort of, so I guess if you think of U as like a heat transfer, maybe. So you have some sort of diffusion, and then well, if you think about it in terms of particle, the BU is some. So that's a way to think about it in a physical sense, I suppose. Does that make sense?
Technically, this is an envelope situation.
Yeah. Yeah.
Steady state. Well, I think it's no diffusion or something.
It's like a scalar. It's a scalar Helmholtz equation. Yeah.
Yeah, it's a diffusion reaction problem.
Yeah.
Well, it's not a diffusion equation if you don't have the time derivative, then it's just an envelope situation.
Yeah.
Yeah.
Okay.
Yeah, I think we need to write the weak formula.
Yeah. Yeah. Let me. I wish I had a whiteboard or something. Yeah.
sorry, just to could you sort of tell us basically what you're trying to do? Is it just minimal surface equation or what are you trying to do?
So this is just a mathematical example. This isn't. It's about how to take a given equation and turn it into a Moose code, and use Moose to solve that. Building on the earlier steps that we covered this morning. Yeah. So if you're kind of lost, then what?
Just a mathematical.
Sure. Yeah. Okay. So everybody, I'm gonna work through the example really quickly, and so in a little bit, I'm gonna kind of walk you through the problem, and so that you'll have some resolution if you're kind of stuck.
iPad where you can write.
Oh man, that would be great.
I can try to set it up. 1 second.
Okay.
HDMI
Like 2?
2. We need HDMI cable. There's an extra one. I never moved it out of here. Perfect.
Yeah, he left it just in case we needed it.
Hey, David. Toss me that adapter. What's that? The button. Yeah, and as soon as we get this going, let's go with this because I think you lost him. You're going to lose him. Maybe I'm just not as patient. Once again, I'll be the one learning the lesson.
I mean, like, I really, personally, I really enjoyed this example during the first time I ever took it.
There you go. That's awesome, man. All right.
Okay.
Hope someone's watching the live stream. Should be coming through on the live stream. Yeah. Yeah, go ahead and start rolling. If you need an extra page. Oh, come on.
Let me,
Good. Okay. So let me close this. Close this. Okay.
actually. And, yeah, so. Okay, so then. Sure.
Sometimes the problem that I'm interested in the moment is coupling full electromagnetic solver in the frequency regime to a very simple plasma model, the root model, and that is 1 billion block.
All right, everybody. So I was going to try to walk through a little bit of this. Forgive my atrocious handwriting on the digital whiteboard. So, thank you so much. That's the wrong thing. This term is that's ready to go into Moose. We don't need to do anything with that. So this would be that reaction style term that I was saying earlier. Then you'd be modifying it by multiplying it by a boundary condition that we're performing there instead of just a first. And we'd ideally like there to be a first derivative. So let's break that up using integration by parts. And we're going to say that, let's see. Whoops. So the result of this is the gradient of your test function multiplied by so this first term here, that would be your diffusion, and so that would be a surface integral of or actually, that's wrong. This would be your yeah, that's what I was trying to do, and then I kept erasing it. So now you have your diffusion term, you have your BC here. So as you can see, this part here, so this first part. So this is a Moose reaction.c. Then this we need to come up with the full form of this residual from diffusion. Then we would be able to say, like we said before, we would be returning d times diffusion compute QP residual. Root of 1 plus the norm squared of the gradient of u. So times the rest of it. So this, all you need to do here is to inherit from diffusion direct as well as its gradients. And so you don't actually need to add any parameters here. For the boundary condition, we can use a constant, I think it's constant Dirichlet BC or function Dirichlet BC. A specific form of the Dirichlet boundary condition in Moose that accepts a function. Well, when functions or function parameters in Moose, remember they can take a default form. So in this case, that default could be a constant number, and Moose would interpret that as a function that is constant over your entire domain. You're just inputting a number as a parse that. Sigma, and you could pass that your value for sigma. So really, the only code you need to modify is that custom diffusion kernel. But everything else is stock in the framework.
So I would be curious, like here, it's a nonlinear problem now.
Sure. The initial guess by default is 0. And you see that when you open pair view and you look at your 0th time step in pair view is 0. If you want to put an initial condition for a particular variable, you would, and can I go to a new page on this thing? Like a blank page? Oh, great. So then I have my variable u. And so I give it, an order, a family, but I can also give it an initial condition. And that's something that we haven't been able to cover yet. Function Dirichlet-BC earlier, it's an integrated boundary condition because it's a Neumann BC. That was my mistake. I was thinking ahead of myself. So when I said function Dirichlet-BC, I meant function Neumann BC, and that is the one that you should use. Sorry about that. So anyway, back to your question. You can give it an initial condition. So that can be a constant. Change that on the fly in your input file. So was this helpful at all to folks? Did it clear up some things? Maybe. Okay. So now I'm gonna move to implementing this. And let's see. So d equals. Oh, okay. Yeah, if you want.
So as a suggestion, I'm thinking that we should solve the PDE first with du equals 1, because you don't have to implement actually any code. So we would just build an input file that would solve our PDE with du equals 1. When we have that, then we would go and actually implement the diffusion kernel with the special diffusion coefficient. So we would break this into two, and we modify an input file to actually use the new code. Okay?
Yeah, that's a good suggestion. All right. So, yeah. So in that case, let me go ahead and let's step through. So I've built I wish I could mirror the display. We're watching, and not on this, I think. So, yeah, it's got the touch bar. I mean, I know how to do it. I just had to take a minute. Yeah. Okay, great. Okay. So then I just.
You're still truncated on this, so.
Making a new kernel. But so I have this application called that I've named Canary, and I'm going to we'll follow David's suggestion, and we'll get started by making an input file first. So I'm going to create a new file, and I'll just call that example.i. And so we're just making a box so we can get away with doing type generated mesh. Then we want a two-dimensional box with the default for xmin and xmax and ymin and ymax, that by itself. And so now we want to make our variables list. So in this case, I'm just going to call this one u and leave it as the default first order Lagrange. So now we've got our variables in place. And so now we're going to put in our kernels. And so Diffusion kernel for now, and let d equal 1. And we'll set the variable to be u. Say that again? So if we go back to this term here, so if d was 1, then we would just have a Laplacian operator there. And so the diffusion, and so if d is equal to 1, then we just have a Laplacian, and then we can use the stock code. Yeah. Okay. And then we have our second term. So, like I said, there's the reaction. That was not what I wanted to do. As a matter of pure coincidence, we happen to have the reaction kernel open when I opened up Moose. So again, this just represents a consuming reaction term with a coefficient of, there's no coefficient, so it's coefficient of 1. Basis function and integrate, we have that weak form. It's just now we have a little coefficient in front of it. But in this case, we've said that coefficient is 1. So for the purposes of this example, we can get away with just using the simple reaction kernel. So you have your test function here times u for your residual contribution, interpolated solution. And so then you have your test function times your basis function, which in this case, they're the same function, but for the purposes of the code, they're labeled differently to differentiate them to like what you're doing on what you're seeing on paper. Makes it closer to what you're seeing on the paper. Okay.
Is this, like, because here we don't have the time-dependent probe, this is called the reaction.
Partly it's a different naming convention as a result of like where, as these pieces of bits and code were developed, they were given a name based on their initial use, and so those names are just kind of stuck there. Yeah. So that's a quirk. So sometimes that adds a little bit to the learning curve. So now we have all of our kernels, but now we need a BC. And so I'm going to name that, Neumann. And we're just going to call that a function Neumann BC. Function that we provide it. So because that is a parameter that has the ability to if you were to create this, you could have a default that is just a number, and Moose would parse that and interpret it as a constant equation, or a constant function. But in this case, you can do that directly in the input file. So I'm just going to tell that is sigma. So we need to go back in and specify a boundary. So in this case, we've got 4 boundaries that we need to cover. We could go through and say 1 for the left, 1 for the right, 1 for the top, 1 for the bottom boundary. But Moose allows us, which is if you were just learning this, that's probably what you would do. But if you could say left, right, top, and bottom, and when Moose parses that, it knows what I'm talking about. So we have our mesh, we have our variables, we have our kernels, and we have our BCs. Now we need to set up our executioner, and this is so then our solve type, we're just going to do PJF and K. Preconditioned Jacobian free Newton Krylov. And then we'll set some pet C options. So PC high G as the answers for these things.
What happens if you don't do that?
You don't, for this problem, it's not really needed, but I generally use it for elliptic style problems. But for a problem as simple as this, it's not really required. I almost do it out of force of habit. So that's
What's better is that the algebraic multigrade.
Yeah, I
So
know
if
what
you're
I know what it is.
solving something that has a diffusion term, then that's the best precondition you can use, and it scales really well in all that stuff. So that's why he's using that.
Yeah.
And you're gonna see any difference on that.
Yeah, so that was a mistake that I made earlier. I didn't specify the number of cells. So I have to go back and do that. Or else we would have figured it out really, really quickly that I made a massive mistake. So so to wrap this section of the code, the input file up, we have our outputs now, and we're saying Exodus equals true because we want to output an Exodus file so we can read it. And so now we'll go back up here. Okay.
You get boomerang spelled again? Scroll down.
It's Boomer AMG. Yeah. Algebraic multigrid. So, nope. So now, let's go back to Canary. And I'm going to run this. -opt-i space example.i. So that runs pretty fast. And so we can take a look at that in pair view and see what we got. How do I rescale that? Solution that that input file takes. So that is with d equaling 1. So now we have solved the problem in a case where we didn't have to write any new code. But now that we've got that, we need to create.
So for your reaction term, the default coefficient is 1 or so?
The default coefficient is 1 because you don't provide it. You don't. There's no parameter to define a coefficient. So in this case, since we have coincidentally defined our coefficient as 1, then we don't have to write new code. But if I said it was 2, or something, our constant times reaction and compute QP residual for the return for that. So does anybody have any questions up to this point?
So in the code, there was this mention that the d of u was 1. Sorry, I missed that.
So usually to start at the simplest possible point you can, and then add complexity. So in this case, we wanted to try to do as much as we can without writing any new code.
Yeah, I understood that part.
Sure.
I just wanted to see in the code where you mentioned d of u as 1 in the text editor.
Okay. Sorry about that. My apologies. So, because we're using just a efficient, and so
Stuff like this, I mean, I understand it now, but I might forget in the future.
sure.
So maybe this can be one type of input, maybe in the notes or in the documentation release, maybe if you can have
Okay.
something like that.
So I guess you're saying it's some sort of explanatory slide in this section of the talk about going through this.
Yeah, and all.
Mm-hmm.
But if I go back, I'd like to know what's the mapping of different things and how you get together all the things into one to run the code.
Okay. So just a way to think about
Yeah.
building one of these things. Okay. All right. So if we were to add, so let's go to Moose. So now we're in Moose, and if I was to go to Framework, and then Source, and then I scroll down here and I find kernels, and then I have Diffusion. So now we're looking at the Diffusion code that's represented in the input file there. Add test for the Jacobian, and so you're not taking in. So if you look at this part where you're taking in your parameters, we're not taking in a parameter from the input file. So we only have a class description for documentation purposes, but we're not taking in a parameter. We only have the default parameters that a kernel has anyway, which is only. So So this we can, does anybody have any questions about this code before I go away from it? Yep.
Could you explain the part about the Jacobian again? Get the first ones are U.
That you're multiplying through. Grad phi is the basis function that you're interpolating the solution that you calculate at each of your nodes. That's the basis that you're creating your interpolation function from to get your final solution, your solution across all space. So phi is just your basis function. Now, because we're using, for the purposes of notation, it's useful to name them differently. Yeah.
And then they exchange iteratively or something like that. Is that philosophy, like in Galarkin? Like you interpolate between solutions, right?
Sure.
In the nodes. And you said both the interpolation and the test function is the same, is one on the
Phi and test is that when you actually run a system of equations and each of your variable has a different finite element type, your phi is going to be different when you're doing the Jacobian, the off-diagonal Jacobian block. Okay? So something needs to happen inside Moose so you get.
And it's easy in this case because we are taking the derivative with respect to u sub j and getting this. Now, when he said off-diagonal Jacobian, that refers to situations where you have a coupled variable. So say, instead of grad u here, we had grad coupled. So whatever our coupled variable is. And so the Jacobian, because your solution variable u isn't involved in that in the residual expression. However, it would have an off-diagonal contribution because you are coupling to another variable in your matrix, essentially another in your system. And so when it builds that matrix, there's going to be a contribution off of the diagonal. That's where off-diagonal Jacobian comes into play.
Could we just once try, in your example, if you remove the reaction term,
Hmm?
it should be ill close. Can you try what happens then?
Sure.
What happens is that we will get a solution, but it's just going to be wrong.
So I'm going to comment out that. Yeah, actually, it doesn't converge. So aborting is solved to not converge. So yeah.
So the math is right. This is exactly what you want to have, right?
Yeah. We've built a basic structure for going to the next step. So now the next step is we need to put in what our value is for d. And so d equals 1 over the square root of 1 plus the magnitude of the gradient of u squared. And so if we go back to my Canary project, and I was working on this just a little bit ago. And so grad u is stored as a vector. Square the sum of the squares of each component, and then the square root of that. But because we're squaring that term as well, then we just have the sum of the squares. So 1 plus the sum of the squares, and then we're taking the square root of that. So this is C++ for, we're pulling it from the standard C++ library, and it is the square root function parameters, because the only thing we need to have here is grad u. And so it's as simple as that. So we have our d term here, and then we're multiplying that by the compute QP residual from diffusion, and then I.
So you've written it here for like a 3D Diffusion scenario?
Yeah, so I've written it generally, and if I'm not using if I'm not in 3D, then the third dimension is just zeroed out. Yeah. So you try to write your.
Along the third dimension would be 0 to do 2D, and you want
Yeah. I could have done this without this much typing. Because libmesh is the underpinning, there's a function in libmesh to take a vector and find its magnitude. So I could have used that and saved myself this typing, but I'm doing it to show the way that this is constructed. And so now we have Jacobian, or Jacobian. Okay. Okay. So now I've saved that. So we've created this new code, and so I need to rebuild Canary.
Comment your stuff?
What?
Did you uncomment your stuff?
The reaction term, you have to comment the reaction term.
You commented out something that made it go.
Yeah. Yeah, I have to fix my code. I broke it. What did I do? Oh, I was in the middle of making this change when we started this. So what the mistake that I made here is I used a template to make this. And the template automatically inherits from kernel, because when you're making a custom, a brand new kernel, you always inherit from, at the very least, kernel. So I made the mistake of not changing that inheritance instead of public kernel. So other than that, those are the only changes that I need to make. So let's try this again. All right. So everything built successfully. And so now we're going to go back to the our input file. I'm going to uncomment reaction. And now we'll see if we can run this again. Uh-oh. Haha, okay. I made another mistake. That's right? It's named Canary. Should be Canary app. Right. Well, so the important error is the one in red. So Moose is saying you have an object that's essentially not being registered correctly. It doesn't know how it's registered, and it is telling you what kernel is the problem, and that you're saying that it's registered to Canary app, but it doesn't know what Canary app is. Sure. Say that again. Oh, okay. That's my problem. It is case sensitive, yeah. So I have to rebuild because I had to change my registration view. I can actually just refresh the file and it'll send me the new data. So to do that in peer review, you right-click on your data file and go to Reload Files, and then Reload Existing Files. So that is the final solution of our example here. And if we go back to the slides, yeah. Yeah, sorry. 7.7, 7.6. Let's see what the range is. 0.76654, 0.86651. Well, I mean, so I'm looking here. So, well, yeah, it's a different color map too. But
So it didn't change.
yeah, it didn't change. So, because so I guess I was actually, so that this is a problem that has been used before, and I repackaged it for this example, and this is the answer that we've that I've so I didn't know that they were the same. Yeah, for sure. Yeah. Yeah. So if we make it bigger, it'll probably yeah. So let's do that. So for a unit square, let's go back to my atom. And so if we go back and y max 20. I'm just making this and seeing, because there should be your gradient should be different. So then I'll just give it a decent resolution, and then we'll run that again. Okay. Now I'm actually going to close this out this time since the mesh has changed, just in case it influences anything. Yep, and there you go.
So one thing I don't really understand, in your input file, you specify Neumann boundary condition for U,
Mhm.
but in your definition of the problem, you specify a condition for D.
That's because what the mathematical expression is. So you have d dot the grad of u, or d times the grad of u dot the normal equals sigma. So in your weak form, you have d times the grad of u dot n times your basis integral is now just sigma. And so we now have sigma times our basis function. And so that mathematically is the same form as a Neumann condition. So we don't need to use d. We don't need to put d in there because we've already defined that expression as a. Well, but because the structure of the equation creates a boundary condition term in the weak form that you can easily replace. Like you have information about d times the gradient, so you can replace that expression with sigma, and then it becomes.
So when you put in boundary condition information, it's not necessarily for the variable, but it's for the actual boundary term that you get in the weak form.
Yeah.
So the way how to think about it is that like you define a variable and you put your PDE on that variable, right? So think of a situation where you would have two PDEs. This boundary condition or this surface term is going to be part of this PDE.
But not necessarily that variable.
Right. So, does anybody have any questions about that example? Yes. So, whenever you're running an input file in Moose, first, of course, make sure that your application's been built. So make -J and then the number of cores on your machine. And so in my case, it's already been built, so it's not giving me any more information. And so then the run command is always your executable run.i. So example, in this case, .i. And then when you run it, and then the Moose runs it for you. Sure.
Can you go through the steps to modify the diffusion kernel?
To modify the diffusion kernel? Okay. So yeah, we have a blank slate here. And I'm going to go ahead and fill this in with a stock template. Okay. So we have our template here. And we are going to, some people use Vim, some people use Emacs in our group, and some people use Atom. And Atom has extensions that are able to have templates for Moose because they've been developed in-house and distributed. So you can download Atom and download Moose language, like color maps, along with Moose predictive text to create using Atom, and it speeds stuff like this up quite a bit. So okay, so we have this template here, and so I've just filled in. I'm including the header file for this source. I've given it a name in my registration for my register Moose object. I need to fill this in with the name of my application, Canary App. then it's inheriting from diffusion. So now we're as far as the C file goes, we're ready to go in terms of modifying it as we need to. So first off, we know so we need to return. First of all, we need to return the contents of diffusion. If we go back to Moose, that's what will be multiplied into that term. And so then we come back and we say, okay, we need to multiply this by that functional form. And so it's 1 over. So the, actually I need to do that in parentheses. We need to have grad u, and we need to take the absolute value or the magnitude of grad u. So we have grad u at a given quadrature point. And we need the x component of that because, as I said before, it's just to generalize it. It's not because we have a three-dimensional problem or anything like that. And so we have our terms here are, I'm just going to copy and paste these now. So when you x in Moose, so true for the other coordinate systems. The first term in the coordinate system is 0, the second is 1, and the third is 2. Or the second and third, I mean. Okay, we need to do one more thing. So we have to end that with a semicolon, or else we'll get an error. And let me make sure I have closed all of my, nope, I need to close one more. Okay. And so I've saved that and crunched it down so you can see it all on one page here. So we're taking the square root of the sum of the squares, and then we're squaring that. So it's just the sum of the squares of the components. Do that, and then the header file is from the default. Yep, you're welcome.
Have you shown where the coefficient sigma is equal to 0.2 has been set up?
Yeah. So in the input file. Down here in our BC section, you have function Neumann BC, and we're just saying that the function in that residual for it once, you could separate it out into 4 different boundary conditions blocks if you wanted to, but you don't have to do that. Go ahead.
Now that we have nonlinear diffusion coefficient, you also should have a more complicated Jacobian.
Yes.
How does it come?
So in this case, it's only more complicated because we have this brand new, taking the, I believe since we're taking the magnitude of it, it's a constant now, right? Not a constant, but it's a, yeah, it depends on you, yeah. So you would have to now go through the process of taking the derivative of that with respect to the
do it. So he is using the precondition JFNK solve, and for that you don't need exact Jacobian, you just need an approximate. So he is throwing in approximate Jacobian, and it's enough for the method to actually give you a solution. If we change this solver into Newton, it would converge probably to a wrong solution.
Yep.
You know, so if you really wanted to use Newton's method for this, you would really need to take the derivative of that.
Or saying, you know, literally throwing this coefficient in front of the diffusion compute QP Jacobian, and the system would handle that and give me a solution. But yeah, if I wanted to use Newton with this, I wouldn't be able to do that.
So the logic is you have linear convergence anyway.
Well, if I'm not going to statements to be fleshed out, you want to actually go through the process of making them. But if you're just trying to get a result, sometimes your problem allows for it, you can get away with doing this. But you should create Jacobians ideally. Now there is a new Moose system that is brand new as of last week. It's an automatic differentiation system, and so it's so new that I don't even know how to use it yet. And it can take your residual and automatically create the Jacobians for you. You just need to give it a residual statement, and Moose will take care of the rest. So, are there any other questions? All right. Well, let's take a short, like 10-minute break, and then we're going to continue on to some of the other sections. If you have a really burning question that you think of in the next 10 minutes, feel free to ask me or one of us.